Okay, so for the rocket design, there are some key ideas you should research, and they involve understanding some basic physics. And so, one of the key ideas is the center of mass of an object. So, the center of mass, also called the center of gravity, either one is fine. And basically, not only that point, this is the point in a body which all of the weight of the body can be considered to be acting. So for the human body, for example, this is just below your navel, and essentially that is where, you know, your whole body's mass can be considered to be acting. For the rocket, it will be slightly towards the lower end of the rocket tube because of the extra mass that the engine has. So that's one important point. The second important point is the center of pressure. And this is the sum of all the aerodynamic forces acting on the rocket as it passes through the air. So what can you do about these points? Well, the key thing is to keep your center of pressure behind your rocket, behind your center of gravity. So if this is your rocket tube and this is the engine here, you'll have some sort of nose cone given to you at the time, but the fins need to be such that you keep the center of pressure point behind. If this is the center of pressure here, and this is the center of mass, we'll just say center of mass, this is center of pressure. So you want this configuration, and the way to achieve this is to think about where your fins should be and how big the fins should be. So fin design is important. This is one of the key things you need to think about when you're designing your rocket. Other important physics about designing your rocket has to do with the amount of material. Obviously, you're given cardboard, and you're given fairly lightweight cardboard, fairly lightweight plastic flute board, and that's important. And the question is why? Well, it all comes down to the idea of net force. Okay, the symbol is F net, and the relationship to forces acting on the rocket. So if we just consider the center of mass of the rocket, as I said before, this is where all the weight of the rocket can be taken as acting. So weight is a force due to gravity, and that equals mass times the acceleration due to gravity, which is fixed, of course. On Earth, it's the value of Earth's gravity is about 10 meters per second squared. Acceleration due to gravity. Okay, that's what that is. The mass of the rocket is the thing that you can control. So, this is important. Why? Well, what is the upwards force? The upwards force, of course, is the rocket engine. And the difference between these two equals the net force. So you want to give as big a net force as possible, and the reason for that is that net force is related directly to acceleration. Acceleration, as you've probably understood, is net force divided by mass. So in this equation, if we can make the net force as big as possible, we can have a greater acceleration. Simultaneously, you'll see masses there again. If we can make the mass as small as possible, we will again maximize our acceleration. So because the rocket engine will burn, that's pretty much a fixed force. You can't really change the size of this force. This is pretty much fixed. But you can definitely minimize your weight by minimizing the mass. So part of your design and build will have to consider how to minimize mass. This includes things like the parachute strings, the fins, the size of the fins, the length of the tube. All of these things need to be considered. Okay, in the next part of the rocket presentation, you're going to compare your rocket data to the model rocket data. But because of the coronavirus, we haven't got the chance to build it and do this straight away. You're going to just simply have to look at that sample data and interpret it. So what does it mean? The shape is kind of like this. And so you're just going to have to understand graphs of motion and apply your knowledge of graphs of motion to what this shape and different parts of the shape are showing. In fact, right at the beginning, I haven't done this very well, right at the beginning, it wasn't perfectly straight. If you look carefully, you will see a slight curve. Oops. Try and fix that a little bit, and maybe a bit more like this, and then a straight part here. So what does the straight part mean? What does the curve mean? What does this curve mean? Etc. That's what you need to do for that slide. And you're going to have to leave your comparison for later, but afterwards you're going to see a whole lot of stuff about SpaceX. You're going to have to watch a video, get the data down, plot a graph, and then analyze that graph. And you should be able to do this by applying your knowledge of graphs of motion that you've been learning. And to help you with that, of course, there is the resources, the Notes Quest resources chapter from Physics for You book. But we've been discussing analyze, there we go, it's better. Okay, so watch the video, get the data, plot the graph, analyze. And it's pretty clear what you need to do for the SpaceX data video. That is the bulk of your work, really, for this rocket project. And so understanding Viti graphs is the key here. So the basics of Viti graphs, one more time. This is the main thing to understand. If your graph ends up looking something like this, which it will, it looks a bit like a triangle. It's not quite a triangle. You're going to have to interpret it, approximate it, I should say, as a triangle, just so you can get things out of it. Just extend the axis a bit. So basically, it might ask you what's the average acceleration. So you're going to have to get a straight line and approximate that curve as a straight line, and then find the gradient, as you've learned by doing rise over run for that part of the graph. That's, of course, how you can find acceleration. Then you're going to have to find the area under the graph. Again, use the triangle line you've drawn. It may not be quite that big, of course. It may stop here somewhere. Depends on what time they ask you to do it to. I can't quite remember. Let's say it was up to this point here. So you find the area there. That area, of course, equals the distance travelled. Another part of the video will ask you to compare displacement and distance. Now displacement is actually distance from a point. Let's say you do a 300 meter race. You start here, you go around the track and you stop there. Finished. You've run 300 meters. That's the distance you've travelled. So distance is 300 meters. But your displacement is actually the difference between where you finished and where you started in a straight line. So you get a straight line and measure that distance. It will be less than 100 meters probably, because of course the 100 meters would be the curve around like that. So that's the difference between distance and displacement. Displacement is a vector quantity. There's another difference. Distance is just a scalar quantity. Other parts of the analysis of the SpaceX rocket, you're going to have to remember how to calculate momentum momentum and change of momentum and how it relates to force. So you've already understood that force is, or for net force more correctly, is mass times acceleration, but also it's related to change of momentum, as you've seen by this equation. So the net force multiplied by time is equal to the change of momentum, which can be written as m delta v. We're not usually changing the mass too much. We're mainly considering the change of velocity. And so that's another part of the SpaceX analysis, which is pretty much the end of the rocket presentation.